camera.
Okay, I am sharing the screen, and
yes, we see your screen. Okay.
I will try to go full screen, and I hope. Okay,
yeah,
first of all, thank you very much for the opportunity to talk about Camelot at this workshop. Camelot stands for Cubesats Applied for Measuring and Localizing Transients. We came up with this mission concept together with András Pál in the spring of 2016, just after the failure of the Hitomi satellite. We're talking about what kind of breakthrough science could be done with nanosatellites. And we came up independently with a mission design that is very similar to Hermes, but our thinking led us to a different detector concept, which I would say is really complementary to Hermes. Our detector doesn't have the same kind of time resolution as Hermes, only 0.1 millisecond, and it also doesn't have the same wide energy band. We only go down to about 15 keV, 15, 20 keV or so, but it allows to make detectors that are big, that have a large surface area, large effective area at 100 keV, and it's a very simple detector that can be easily placed on other satellites as a secondary payload. So one can easily envision potentially also flying a detector on the same platform in the future together with the Hermes detectors. So today I'm going to talk about our first demonstration missions, which will be launched early next year. We will have one dedicated demonstration mission on a 1-unit CubeSat, and we will fly 2 detectors as a secondary payload on a 3-unit CubeSat, on the Czech 3-unit CubeSat called VZLU Sat-2. On the development of this detector prototype, most of the work has been done by people who are here shown in a boldface font. András Pál, Masanori Ono, László Mészáros, Jakub Zsipa, they all worked very hard in preparing these detectors for these demonstration missions. Camelot was initiated as a Hungarian-Japanese collaboration. So we have many both senior Japanese colleagues and students. From this project, we already have several master theses. And among the names here who really contributed, you also see our Slovak colleagues, Jakub Kapuš from Spacemanic, Robert László from Nidronics, who helped us to really make these flights, who contributed to the platform side. So let me first tell you about the Camelot concept. So we came up with the concept of having 3-unit CubeSats, 9 of them in 3 orbital planes, 3 satellites in each orbital plane. Each satellite equipped with 4 cesium iodine scintillators of a size of 150 times 75 times 5 millimeter, read out by silicon PM detectors by Hamamatsu called multi-pixel photon counters, or MPPCs. And the goal is degree scale timing-based localization with a good sensitivity. Each satellite shall be equipped with GPS receivers for precise time synchronization and with inter-satellite communication capability, providing all-sky coverage with a large effective area. So in order to maximize the effective area per CubeSat, we came up with the idea of placing thin cesium iodine detectors on 2 perpendicular sides of the satellite. Each detector should be of a size of approximately 8.3 times 15 centimeter, and the cesium iodine itself is 5 millimeter thick. And each of these thin, relatively large area scintillator plates shall be read out by these multi-pixel photon counters. So it's quite challenging to actually read out such a large thin detector with a small readout area, but our colleagues in Japan demonstrated that it is really possible and that this concept is feasible. Jakub Žipa in our team also made studies of the expected particle background on the low Earth orbit. So when we were doing our feasibility study, we assumed two kinds of orbit, either polar orbits or orbits with an inclination of 53 degrees. The reason for that was that these are the orbits where one can most easily find launch possibilities today on the market. And Jakub showed that for these orbit inclinations, one has a duty cycle of around 70%. So here you see a graph of inclination for different altitudes, 500 to 550 and 600 kilometers for duty cycle at different inclinations. And you can see that both on polar orbit and on an orbit of around 53 degrees where Starlinks are placed, you have a duty cycle of around 70%. So where do we stand? So first we performed the feasibility study and developed our detector concept. Then we decided that we will go step by step. So we had this nice plan that we develop a detector prototype, and we will first fly it on a high altitude balloon. Then we will put a detector on a 1-unit CubeSat, and then we will fly 2 detectors on a 3-unit CubeSat as a secondary payload. However, the coronavirus crisis came, and in March this year, just 1 week before we wanted to do the balloon flight, the borders were closed down, so we were not able to do this high altitude balloon test. And after that, we really got under enormous time pressure to actually finish our detector for this 3-unit CubeSat. The launch of the 1-unit CubeSat got delayed. So the our first detector to fly will actually be on a 3-unit CubeSat called VZLU Sat2, which will be launched by Falcon 9 in no earlier than mid-January next year. And then no earlier than in March, we will have our second demonstration flight on a 1-unit CubeSat called GRBALPHA. It will be launched on a Russian Soyuz rocket. So this is GRBALPHA. This is a 1-unit CubeSat where our detector is placed on one side of the cube. It has a side of 75 times 75 times 5 millimeter. And it is a scintillator enclosed in a 1 millimeter thick aluminum, read out by multi-pixel photon counters. There you can see there is a lead shield which protects the MPPCs from proton damage on a low Earth orbit. This CubeSat is based on the first Slovak nanosatellite called SK-Cube, and we were helped by the Slovak companies SpaceManic and Nidronics in building this satellite. And the satellite shall demonstrate our detector concept, and because the detector concept will be same on Camelot, just the detectors should be there bigger. So this was our plan. We planned to first launch this basically CubeSat model on a 3D printed frame. We plan to launch first to high altitude on this kind of a meteorological balloon, because this is simple, it's easy to launch, it is cheap. It can fly at an altitude of 38 kilometers for 6-7 hours. And you can test your equipment. Unfortunately, we didn't do this in the end. So this will be our first demonstration mission. This is VZLU-2. This is an actual picture of the satellite before its delivery to the United States. VZLU-2 is a technology mission of the Czech Aerospace Research Organization. It has an Earth-observing camera as a primary payload, and our detector is placed on two sides, two perpendicular sides surrounding the camera. There is space for it at the bottom of this picture. And this flight shall demonstrate our detector concept, shall flight test the multi-pixel photon counters, the superstructures, the electronics, software, data handling, everything. What is also interesting, solar panels are placed on the top of our detector. These are specially developed solar panels with no copper, so there is a lower absorption. We will lose about 20% of photons due to the solar panels having on our detectors, but it is a small price to pay for the ability to actually fly our detector as a secondary payload. So in the future, this might be the way. What is our detector? It's a cesium iodine scintillator. You can see it on the left. Again, size 75 × 75 × 5 millimeter for these demonstration missions. It is wrapped in ESR, and it is read out by 8 MPPCs, 2 readout channels, each channel with 4 of these multi-pixel photon counters. On this readout board, you can also see 3 thermometers, so we know the temperature and the temperature gradient. Then this readout board is attached to the scintillator using optical rubber. You can see it on the right-hand side, and it's attached using optical rubber in the case of VZLU-2, and in the case of GRBALPHA, it is attached using the optical glue of the type that you can see written there. Here you can see Jakub Žipa and Masanori Ono as they are defoaming the optical glue, and they are just gluing the detector to the cesium iodine scintillator for GRBALPHA. So on this picture, you see on the left-hand side the ESR wrap scintillator with the attached MPPC board. And on the right-hand side, you see that we've wrapped this MPPC board with a Tedlar DuPont shield to prevent any light leak into the detector. Here you see this Tedlar and ESR wrapped detector placed into 1 millimeter thick aluminum casing, and you see 2 cables coming out for the 2 readout channels, and they connect directly to the analog board, which is, as you can see, very close, and then the cables only take the digital signal to the digital board, which is further away on the satellite. On the right-hand side, you see that there was additional wrapping necessary around the this MPPC board before closing the aluminum casing. This has been done by Masanori Ono, and he applied really serious origami skills to actually wrap this well so that it fits nicely, tightly into the aluminum casing. The MPPCs are really sensitive to proton damage in the low Earth orbit in the South Atlantic anomaly. So they need to be protected, and therefore we have a lead shield placed around the side, around the place where the MPPC boards are. And our Japanese colleagues Masanori Ono, Hiromitsu Takahashi, together with the student Kento Torigo and other students at Hiroshima University, they did also beam tests on MPPCs in Japan to determine what will be the proton damage. So we are hoping to minimize it in orbit. Here on the left-hand side, you can see the analog boards. These were developed by Masanori Ono. There you can see all the details about the components. And on the right-hand side, you can see the digital board, which was developed by András Pál, and the board was assembled by László Mészáros. You see that there is redundancy. The board has two FPGAs, two MCUs. So if one side of the board fails, we still have the other side. We happily delivered the detector to Prague in August. It was an adventure because our car broke down, and in the end we had to deliver the detector in this rescue car to Prague. And here the detectors are already in the clean room in Prague in the Czech Aerospace Research Organization's laboratory. The detectors weigh 2 times 280 grams plus 50 grams for the board, and the power consumption is 0.7 watt. Here you can see the detector being tested on the satellite bus, and on the right-hand side there is the EM of the satellite with our detectors already put inside, and András Pál is looking at the many cables. So VZLU-SAT 2 underwent very serious vibration tests, also shock test and thermal vacuum test. Our detectors operated well after these tests. So we are hoping for a successful operation also in orbit. This is our spectrum that was obtained using americium and barium radioactive sources. So you can see that the dynamical range is not too bad. We could go down below 20 kV and up to 500, maybe 600 kV. You can see the americium escape line, barium lines, and also the barium line complex around 300 kV. VZLU-SAT 2 was delivered to the Netherlands and then to the United States in September. This is the VZLU-SAT team. We were not able to say goodbye to the satellite because of the coronavirus situation. Only Jakub Žipa was there. So we said goodbye to the satellite through video conferencing. So the further steps that await us, we still have to finish GRBALPHA. This week, the satellite platform is being integrated in Slovakia. On Monday next week, the detector will be integrated into the GRBALPHA satellite platform, and next week on Wednesday, vibration tests are scheduled in Budapest, and the satellite needs to arrive to Moscow by Christmas. The deadline is December 25th currently. Then, because we were under very large time pressure, we didn't have time to completely finish the onboard scientific software, and we will be uploading it after the launch of the satellite. And then what awaits us is operate the detectors on orbit and see that everything works. And the final goal is to have a constellation of GR detecting nanosatellites in orbit, also together with follow-up observation capability. The question of how many GRBs can we see with a small detector such as Dan on our 1-unit demonstration mission? Masanori Ono tried to make an estimate, and he estimated that we will see about 10 to 20 gamma ray bursts per year with this satellite. So something interesting about the future. So The Czech Ministry of Transportation just recently, together with ESA, issued a call of proposals for an ambitious technological scientific mission. Here, the emphasis is on technology because that is what interests the Czech government, and science is second, but one can do really interesting science with this kind of mission that we can propose for. So together with the Czech Aerospace Research Organization, which is a prime, and my group at Masaryk University as the scientific partner, we are now proposing a mission that would consist of at least three microsatellites, possibly supplemented by Cubesats. And what we are thinking about is to have microsatellites which can do rapid follow-up observations in X-rays and in near UV and in near infrared. So we are thinking of having telescopes with a 20-centimeter aperture. So this would be very interesting. This would fly if it gets accepted in 2027, and it would allow us to really rapidly follow up sources that are detected by HERMES, any global constellation of GRB detecting nanosatellites. So there are many.
Norbert, two more minutes.
Yes. So this is my last slide. I just wanted that there are many teams building nanosatellites for GRB detection, and in 2018 we organized a conference in Budapest where there were many people from around 20 countries from all around the world who are interested in doing this, and we can achieve a GRB detecting nanosatellite network together. So this is my summary. Thank you very much for your attention.
Okay, thanks to you for a very nice presentation. I already see questions, so Michele, go ahead.
Yeah, great talk and activities, Norbert. Was wondering if you could clarify what near infrared wavelength range you're considering for your new proposal.
So we are considering something that is similar to what you are proposing in Skyhopper. Yeah. This is the call for proposals put some budget, which is in the Czech Republic 15 million euros. And the most important thing for the industry is to develop these microsatellite platforms. And for us astrophysicists, we need to come up with something that is going to be really, really meaningful. For following up transients, we thought that the X-rays are important to really pinpoint the position in the sky more accurately. That's why one microsatellite shall have an X-ray telescope. And then the UV and infrared are interesting because of the kilonovae, to see how the UV to infrared flux ratio evolves with time early on. So our idea is that this would be the best combination. Now it's a question whether we can build all three microsatellites for this budget. So I think the priority will be on X-ray and near UV, and then we hope that the infrared we can do as well. And we should really talk and work together.
Yeah, we can organize a meeting via Zoom offline to talk more if you're interested.
Yeah, this is still very early on, so we are. The proposal needs to be put in by mid-December. In March, we should know who won. First, there will be 4 teams which will win to make a detailed phase 0, A, and B1 study. There will be 1 year for that, and then the final 2 teams which build the satellites will be selected. So there is time.
Okay, thanks, Norbert.